GIAN program entitled Cloud Data Center Service Provisioning, Theoretical and Practical Approaches, which is sponsored by MHRD, and it will be conducted by our esteemed resource person, Professor Jemal Abawajy from Deakin University, Australia. To start the program, I would first like to call upon our Dean, Professor D.K. Lobial, to introduce the school and to welcome our chief guest.
Thank you, Dr. Zahid, and our honorable chief guest or resource person, Professor Jemal, my colleagues sitting here, other participants. I welcome all of you in the JNU campus, especially in the School of Computer and System Sciences, and for this workshop on cloud computing. This is now, and I'll share some information regarding the school. And this school is the School of Computer and System Sciences, JNU. Is one of the oldest schools in the country imparting knowledge in computer science. It started in 1974. Very few people may be knowing this. And largely, the computer science education in the country started in 1984. Largely. But there are very few schools. This is one of us. And we run 3 programs here. One is the Master of Computer Application, which is a postgraduate program. Then another postgraduate program is Master of Technology, MTech. And then we run PhD here. So 3 programs we are running currently. And now in MTech we have also MTech in statistical computing. That is another we have started just last year. So we have 2 MTechs that way, and 1 MCA and PhD program. And we have a large number of PhD students enrolled with us, maybe around 100 plus currently. And we have 20 faculty members working in different areas of computer science. And largely the broad areas where you work is, one of the areas is the big data analytics, data mining, soft computing. That is a good number of faculty members work on that area. And some of us work in the area of wireless communication and largely computer network. And yes, it is also one of the colleagues working on the cloud computing. That is what the workshop is here, and the group works on that. And some of the colleagues works on MEMS, that is related most with electronics. And some few colleagues may be working on small areas, this, that. So largely 4 areas broadly, that is what we work on. And we produce PhD in these areas. So this is what I said, even in the sciences in JNU, all science schools, this is one of the oldest schools in the sciences as well. So once again, I welcome all of you in the JNU campus, and I wish you to enjoy this workshop as well as the ambience of the JNU. Thank you very much.
Thank you, sir. Now I would like to call upon Professor D.P. Vidyarthi to introduce this particular program and the importance and significance of the same.
Very good morning, all of you. Actually, I am thankful to Professor Jemal, who agreed long back that he'll be imparting his own knowledge, because he's a well-known researcher in this particular area of the cloud computing. Probably if you go through the literature, you will find that a vast number of publications he has made, especially in the resource provisioning aspect of the cloud computing. And he had been helping us in the last mini workshop that we had organized here in the school, the cloud computing workshop, and he has been always our resource person for this particular workshop. So he agreed for this cloud GIAN program also, which is almost in span in the 2 weeks program. And in fact, in the beginning, many registered for this particular program, but I understand that we are not able to provide the accommodation, and it's very difficult to survive for 2 weeks in Delhi, especially in this particular environment, to survive on. So that is one particular reason that many could not turn up, even despite after registering itself. But anyways, this is our problem that we do have to cope with this. The program, as far as this particular program is concerned, every day we will start at 10 o'clock with the tea, and then 10:30 we can start our lecture. Will be 2 hours lecture, 2 hours theoretical lectures by Professor Jemal, and followed by the 1 hour lunch break also. and thereafter 2 hours tutorial in the second half. So every day will comprise of the lectures as well as the tutorials in this particular area of the resource provisioning. So that is the program for next 10 days or next 12 days. We'll have this particular program. So Professor Jemal is having vast experience in this particular area. So he said that he will be starting with the introduction in the cloud computing area, so that even the young researchers or young students who are just going to start their career in this particular area, they can easily understand the cloud computing aspect. So the cloud computing, he'll be starting with the cloud computing, then moving to scheduling aspects, the resource provisioning aspect of the cloud computing, the different techniques that are being applied, the machine intelligence techniques, the heuristics, meta-heuristics, even the game theory which is being applied nowadays quite often in this particular area, that also will be covered by Professor Jemal. So maybe over the entire this 2 weeks program, you will be really equipped with doing some really good research in this particular area of the cloud computing. And as the cloud is expanding to, let's say, many other domains as well, like the IoTs, etc., etc. So I'm pretty sure that you will touch upon these aspects also, that how cloud can be used for IoT related activities, IoT related processing as well. So that probably Professor Jemal will deal with. I'm really thankful to all of you who have come from many other parts of the country as well, India as well. So I'm very thankful to you. And special thanks to Professor Jemal that he is here with us to impart his own knowledge. Thank you very much. Thanks a lot.
Thank you so much, sir. Before asking Professor Jemal to take over the stage and start the program, I would first like to briefly introduce Professor Jemal. Although there are so many feathers in his cap, but I would like to touch upon a few. Professor Jemal Abawajy is a full professor at Faculty of Science, Engineering and Built Environment, Deakin University, Australia. He is a senior member of IEEE Society, IEEE Technical Committee on Scalable Computing, IEEE Technical Committee on Dependable Computing and Fault Tolerance, and IEEE Communication Society. His leadership is extensive, spanning industry, academy, and as well as the professional areas. He is currently the director of the Distributed System and Security Cluster. He has been actively involved in the organization of more than 300 national and international conferences in various capacities, including chair, general co-chair, vice chair, best paper award chair, and so on and so forth. He has served on the editorial board of numerous international journals, and currently he is serving as an associate editor of the very popular IEEE Transactions on Cloud Computing, International Journal of Big Data Intelligence, and International Journal of Parallel Emergent and Distributed Systems. He has also guest edited many special issue journals. He is actively involved in funded research, supervising large number of PhD students, postdoctoral research assistants, and visiting scholar in the area of cloud computing and big data. He is the author and co-author of 5 books, more than 250 papers in conferences, book chapters and journals, including IEEE Transactions of Computers and so on. He has also edited various conference volumes and delivered various keynotes. This is all about his academic things. As far as my own personal touch with him is concerned, when I was doing my PhD, I still remember, since I have cited many papers of his work, or many models that he has proposed for resource provisioning. I remember the first time when he came to GNU in 2006 for a conference, national conference on NCM2 in 2006. So I was really excited that the researcher whose work I have really cited, I was really excited to meet him that time. And since then we have been meeting for maybe we have met a couple of times, and it's always a delight and pleasure to get to know him, get to talk to him, and to listen what he is about to deliver. Thank you so much, sir, for sparing time for us. Thanks. So I would like to now call upon Professor Jemal to deliver his first lecture of the
Hello? Okay. Okay. Hello. Hello. Yeah. Okay. I'll just use this one. Oh, it's coming. First of all, I would like to thank DP and Zaid for their invitation in this GIAN program and a very nice welcome and introduction by Professor Zaid. I think it would be very nice for us to meet and talk about research. I mean, Australian researchers and Indian young researchers as well. There are a lot of things we can learn from each other. I've learned from them many things. Even when I review their papers, I see something very important things that their PhDs and they contribute to the cloud area and particularly to resource management area, which I focus on my research. One thing I want to say though, I came from very hot area into very cold area. And my laptop also died, which is problematic. And I tried to put the lecture this morning because the good thing is the planes didn't let me sleep. So I got up and I decided to work on, I turned on my laptop, refused. Then I decided to put this lecture together as fast as I could. So if it is a little bit funny or it's not showing something, I actually, sorry, I have to tell you up front because I just put this lecture together. I'll fix my laptop today and hopefully everything will be there. Basically what I'm talking about today, yes, as Professor Deeply said, I will actually talk a lot of things that I'm talking about today is about a new book I'm writing on cloud resource provisioning and scheduling. A lot of it is research. Sometimes when I go some places, a lot of people are scared about the maths of it. I will try to not really make it a lot of mathematics in it. I'll give you the maths, even though it looks scary, but it's not really. It is just there to support. Today I'll be talking about basically introduce you to the distributed systems landscape, where we were and where we are now, where we plan to go in the next few years. So this is the roadmap for today, the introduction and the landscape of cloud computing, and I'll talk about a little bit different types of cloud and some example from our work. So you can stop me anytime if you have questions. I'm okay with it. Now, I actually did my studies in Canada, bachelor, master's, PhD, and when I did actually my bachelor's, the distributed system was nothing but really very expensive bunch of supercomputers. But since then, a lot have changed. A lot. When I say a lot, it's really a lot. and it is really changing still. The landscape is not actually static or moving slowly, but it is actually moving extremely fast. So I remember around 2007, 2008, when we were very hot with cluster computing, and all of a sudden cluster computing disappeared. And now, as I will show you, even cloud computing is now going in the background. And I'll talk about that. In particular, if you see here, in fact, it's forecasted 50 plus, not about 20, but 50 plus billion devices will be added into the internet in the next 2 to 3 years. These devices will make actually cloud computing to basically become bottleneck. And the issue is how to actually address this. And that is where the resource provisioning and scheduling comes handy, in addition to other platforms that we need to develop. So I will start with a little bit journey in distributed systems. Before I actually start that, what we see is nowadays we see a lot of data centers. And these data centers have always been there in some size and magnitude, but in the last few years they have become extremely big, and they are distributed in many places, in many other countries. They bring a lot of challenges for data storage, for processing, as well as for energy consumptions. We will look at all these issues later on, but they are always there. Universities have their own small data center, large companies have their own data center. The only thing that actually moved in the last few years is the business model, from owning your own data center to actually buying data center as a service, or buying a part of it to store or computing resources from it. That is the whole thing that changed. Otherwise, the data center has always been there, and we will look at it later on when I talk about data centers in detail. So what has moved in terms of computing? As you can see, people actually fetch water before actually the water distribution network became available. And in some part of the world they still do, but it is actually disappearing. Once the water distribution network became available, so we basically it's just a matter of turning on and off of the tap without actually caring where the water comes from. And what that will lead is also to wastage. We don't actually care, we don't actually know, or we don't actually pay attention to how much water we use, how much we actually we need and we don't need, when we need, and also for. So that is where it comes actually the issue of resource management as well. Not only we have moved from bringing water and knowing that it takes a long time, and making sure that what we bring is put to a good use to the last drop, to really don't care about where it comes from. I will pay for it, but I will also waste it. So that seamless delivery based on what I use and what I pay. And the same electricity. From using some candles with electric distribution system, we just care about turning on and turning off. Now we talk a lot about this in terms of smart grids. And smart grids actually is linked to data center. And so you can see that now we actually use technology to ensure that the wastage and the consequences that this electric distribution system has brought in terms of environmental impacts it has to be resolved or at least minimized. And we will talk about that later on when we talk about energy aware resource management. Again, in terms of computing, we can see that before silos, we do our work, we still do, but unknowingly we are actually accessing a more seamless computing that is available for us 24/7 from anywhere at any time. The issue is we don't really know where these services are. And so, as I said, that as we waste water and electricity, we do waste also a lot of things in here. One is, in fact, if you link it with electricity, sometimes we actually turn on everything and go. And the server is sitting there doing nothing but consuming energy. Our laptop is doing that. Our mobile phone doing that. Everything is actually tied to this. And if you go that way also, a lot of water is used to cool down some data centers. So I am showing you horizontally and vertically these are linked to one another. And the solution, even though now we have actually come up with a business model that I don't care where the computing resources are, where the storage resources are, I am happy to, as far as I can access my photos, my emails, my data, and I will use it. That is also seamless computing delivery, but the issues is that, as I said, in the next 2 to 3 years, there are going to be about 50 plus billions of devices are going to be added to this resource. One of the reasons we moved from the standard conventional computing is because of this issue. A lot of resources needed. Applications are growing each time. Applications become hungry. Then we come up with a new platforms. We come up with a new resource management. We come up with a new provisioning and so forth. So again, as you can see, even though seamlessness is happening, but there are a lot of issues to be resolved. To start with, mainframe. I am old, but I haven't seen mainframe. I never worked with them, but I know a lot of things about it. Some people have actually did some work on it. Basically, what mainframe is used for was a lot for batch processing, like transactions, census data, and so forth. The only problem with it is that you actually, if you come around 70s, in the 60s, they used to have, I think, punch card, and in 70s, you actually write COBOL programming or language using programming language such as COBOL or IBM's own language, and then you submit it as a job to the operator. Operators will run the job and then bring the result back to you. That was actually what we call batch processing. It was good, but some people actually, the reason I bring mainframe is that some people argue that we have actually moved in full circle from mainframe and to cloud computing is actually a mainframe concept. So this is what people are saying now. When you look at it, really, the idea seems to make sense because now we actually submit our jobs to cloud computing and wait for results. The only thing is that the business model is changed. For IBM, you have to work in that company to do this. but for cloud, anybody can do it. The only, again, another thing is that they are, the way service level agreement and quality of service is, is changed. Now, in the 70s, we got parallel computing and distributed computing. There are two different computing. They are basically used for parallel programming or jobs, applications that can be parallelized, or what we call divisible workloads, and they can be used on parallel computing or distributed computing. The parallel computing, you have many CPUs in like 64 CPUs, but all of them share memory. So they have one shared memory, and shared memory becomes a bottleneck in here. Distributed computing have many CPUs with their own distributed memory, but they share the network. Again, the number of machines or CPUs are in the neighborhood of 64. The ones I used, actually, I used both of them. The problem with they're very, very expensive, in $2 million, $3 million. I put them together because they are cost-wise, they were very, very expensive. What nowadays a bunch of standard workstations or servers can do, that's what they used to do, but they're very, very expensive. At that time, they were able to handle the applications as well. If you are a researcher, the day you get access to these systems, as if you won a lottery. Really, really, it's very hard to get access to it unless you work for big companies or work with governments, research environment. So we moved from there and into what is called client and server, where around this time local area network became strong. But again, we have a bunch of diskless clients or workstations and some servers. And then these are sometimes called dummy monitors. And they simply access and send requests to the server through RPCs, remote procedure call, and RMIs. Those were in 1980s. Around 2000, 1999, 2000, cluster computing became very, very famous. We actually called it poor man's parallel or distributed computing. It was actually very, very effective, and I built a number of them myself and used it a lot. Basically, what cluster computing were is a tightly coupled workstations and servers. These servers are actually divided into a slave and one master. So the master node is where resource management and scheduling happens. If anybody wants this slide, I will leave it here. I'll give it to you, okay? If you want. So now what happened is you have a bunch of servers here. They're called slaves, and you have a master node here, and these are workstations that are connected to masters. You don't see this. You just use the master node to create these ones or to actually access these ones. And it was actually very good but very difficult to use. MPI is the program we used most of the time with it, and we did a lot of matrix multiplication type of things, and some real-time applications, a lot of databases, and load balancing, and so forth. So cluster computing actually became very hot when you multiply, when you have multiple clusters connected together. And you have one cluster here, and then you have another cluster. This idea then slowly gave way, connecting 1, 2, 3 clusters to the idea called grid computing. So what basically grid computing was, it allows you to basically use resources from many locations. So as you can see, this is in Bangalore, a cluster, and this is in Calcutta, and this is in Delhi. So Delhi has supercomputing. Actually, within grid computing, I used a lot of grid computing. I never actually used supercomputing. I don't know where, but technically it's possible to connect supercomputing, but most of the grid computing were really multiple clusters connected together from different countries, and in some countries they were able to build up to 5,000 or 50,000, I can't remember. I think France built 50,000 or 5,000 nodes. Now, this is actually tightly coupled. Cluster computing are tightly coupled, and grid computing is actually loosely coupled. So you can couple clusters and supercomputers, and so you can send a request to one of these resources. Now, I didn't want to introduce scheduling here, but scheduling in both here and here is done at 2 levels. So here, it's done at this level to distribute the work to these slaves, and locally at the slave level. That's how we actually do scheduling. The same thing here. Again, this actually does it within 2, but you need to have what we call gateway. So to connect multiple clusters, you need what we build what is called gateway. That gateway actually is used now in Aneka, and it is used in CloudSim, and we used it in many other papers that we have written. We need a gateway to actually send it to each one of these resources. One of the problems when you have multiple resources is heterogeneity. So different types of resources are coupled together loosely, and you actually try to send and expect the response time or the throughput or whatever you want to get at the end of the day is returned at the same time, but you don't get that. And particularly some workload models are not really very good for grid computing. So heterogeneity was a very serious problem. Another problem was actually availability, reliability. Some of them, from security perspective, you don't know what is happening, and some of them actually, if you actually use this one, for example, if the local job is running, this master node is most of the time is designed to look at external jobs and internal jobs differently. to give internal jobs priority and to give less priority to other jobs. So receiving expected output from grid computing was not straightforward. It was a difficult problem. As I said, fault tolerance is another problem because these clusters were running on these servers are actually cheap servers. They tend to fail a lot. So running on these very cheap slave nodes were also risky. So we need to come up with failure-aware resource management or checkpointing or different types of making sure that the job is submitted was actually completed. But completing it on time became very difficult. So the offshore of this grid computing is the data grids, which is another basically it is really based on this. This is for computing and a small data, but this one is for large data. So the idea is the same. So you have computing node here, and then there are storage here. So what you can do is that if you have a lot of storage here, you can distribute this storage, this data from this storage to other facilities, and then run your job on those data. This scientific data was extremely big. A lot of instruments collect very large data set. And this data set has to be actually distributed in somehow, because you can't all access from these particular resources, but you need to ship some of them. It's exactly what Google does now. They have 44,000 nodes, servers, and they place them somewhere. Every time you send a query, they try to actually look at the locality of that query and then get the resource from there. So this is, again, became very hot, and still a lot of people use data grids now. Okay, why we actually do cloud computing? What is the motivation of doing cloud computing? Now, if we look at this, let's say this is non-cloud environment, and if we look at the capacity and time along the horizontally here, we can see that this is actually the actual workload on the system, and this is the forecasted load, and what we get is that this is actually what we waste. This all is what we waste, and the capacity that we waste. This is what under supply of capacity, and this area is all IT capacities. So if you look at all, basically we lose a lot of resources. What I'm trying to say is that 80% of the time our resources just sit doing nothing, whereas we only use about 20% of the resources. So then we came up with the idea of why don't we sell resources that are sitting? Okay, so this idea is actually now being translated into cars. Cars, you buy cars and you use them about 10%, 99% of the time the cars are parked. So why don't we share cars? The same thing, why don't we share resources? And that idea came up with, why don't I sell my resources that are not using them to others on the need basis. So that is exactly what cloud computing concept is. It's a business model, right? Scientifically, the resources are there. It's either either cluster computing or grid computing. But the idea is grid computing is free. You just go in and if it's available, you use. If it's not available, you wait or you search until you find. But the cloud idea says, I know I have this availability, but I will use it. So the idea is to really virtualize. This is our cloud computing, to virtualize, to use virtual technology, virtualization technology, to share the resources. This allows you actually to share the resources and to give you a perception that the resources are unlimited. So that's what basically it does. Even though we know that the resources are finite, but it gives you the perception that it is unlimited. You can use it as much as you want. It can scale in and scale out. This is one of the properties talked about a lot in cloud computing because of the virtualization that gives you. It can go up, it can go down on demand. When your demand is high, you can actually increase your virtual machines. If your demand is low, you can go down. You can do this automatically as well. And you can also here tenancy, you can share the resources with other people and so forth. So cloud computing is the on-demand delivery of computing as a service. You get it as a service and you pay only for the service you used. Okay? These are applications, different types of applications usually. And the hypervisor, again, these are where you create virtual machines and use the virtual machines on the physical machines. Now, we don't know where these physical machines usually located. It could be in Arizona, or it could be in Delhi, or it could be in Beijing most of the time. But that also created some issues. For example, you can't actually take taxation data and move it from outside a country and so forth. But what cloud gives you is, you can, as I said, elasticity is one of it. You don't, these resources are automatically managed and these resources are available for you at any time, and also you can share the resources with others. Now, each one of these brings a challenge, each one of them. So tenancy, multi-tenancy, for example, you sharing, time sharing, for example, a resource. So if you have two virtual machines, then these virtual machines have to share the same. If they are placed on the same machine, they will share the machine, right? So either space-wise or time-wise. Now, if they share, you need to appropriately schedule, right? You're selling this resource. Now, if you're the owner of the resource, you wanted to sell depending on the demand and supply, right? If the demand is high, you're selling it more bidder, or if the demand is low, you schedule it without priority and so forth. But sometimes these applications can actually collide. So in other words, security become an issue, particularly if you're running two sensitive applications on the same node, on the same storage memory. So one can read the memory, whatever written in the memory sometimes. So privacy and security become a problem. This is when people talk about security issues about cloud, this is actually what they're talking about. It's not about availability, auto management, and elasticity. it is multi-tenancy because applications, no tenant, right? You know, tenants are share just apartment, rent apartment, 2-3 students live together, and so maybe if it is, they can also see each other's underwear. It's the same thing here, right? So they can see the data of other person. We talk a lot about security when it comes to grid, cloud, multi-tenancy is an issue. So what is happening now is that if you don't want multi-tenancy, you can actually ask, but you pay more. So price is the issue in here. Okay, so we have seen before the problem of 80-20, 80-90 usage and unusage. So again, if we look, this is what actually cloud gives you. Very close to the actual one. Okay, so reduction of initial investment, you can see instead of paying a lot, you actually don't pay for the resources, for the infrastructures. If you want, you don't even pay for software. It's up to you. So there is reduction in there, and you can see that reduction of oversupply, because when your need for resources, most of the time, the need for resources fluctuates up and down, right? When you need more, if you don't use cloud, you buy. And then once your fluctuation goes down, the resources just sit there doing nothing. But now, because of the elasticity and only paying for what you use, the reduction is obvious here. So again, you save there. No undersupply because you use enough resources in cloud, and also possible reduction of IT capacities in case of reduced load. So when your need goes down, you also the amount of money you pay goes down as well, because you only use what you need. This is actually the selling point for cloud computing, even though these are what we seem to be focusing on. These are the points that actually make cloud computing much more interesting. Now, what do you think the problem with these ideas? Even though they seem to be good, they are issues. Anyone? There must be something we have done right to get this very close.
Identifying the resources.
Yeah, dynamic resource provisioning is we must have to do something, because you can't actually get very close to the actual, right? So dynamic resource provisioning is very, very important in cloud computing. Without dynamic resource provisioning, there is no way you can actually do this. We know this part because instead of buying, let's say, a rack of storage, because you need, you're collecting a lot of Twitter's data to do sentiment analysis, and once you finish the sentiment analysis, the data is gone, the storage remains. So instead of that, you collect your data in the cloud, and you use the data. You get you do the sentiment analysis. You throw the data. You use the result. You act on the result. Then you pay for whatever you used. So that is where the reduction in terms of cost comes, right? Purchasing cost, but reduction of oversupply of resources is obvious because I'm not buying something new, right? I'm just using what's there. I don't oversupply or undersupply is because I'm using the resources. Underneath that, the cloud service provider himself uses a lot of dynamic provisioning in terms of also price. The supplier needs to recover their investment and make more money also. So they need to actually make sure that the resources, the pool of the servers and storage they provide will be working most of the time, right? And that is what dynamic resource provisioning gives you. So it makes the resources, whether they are processors or storage or networking, to work. Now, when you look at the dynamic resource provisioning that does this, there is also additional cost. Now, these additional costs come from data centers' energy consumptions, from some employees in there. So that is where you also take into account, the cost due to energy, the cost due to some employees, the cost also due to some failures. Sometimes the resources fail and you quickly need to do what we call now migration of virtual machines to other machines, turn off some machines and so forth. It's not simply scheduling workloads and sleeping. That is what it used to be. When you do resource provisioning, you simply provide, select the best resources and submit. Not now. Dynamic resource provisioning, it is actually now is proactive as well as reactive. So it works in 2 dimensions. And it never simply looks at the queue of the jobs available. It actually now looks at resources, the SLAs, service level agreements, quality of services. It is actually now does many things to get this nice alignment of actual resources or actual load. I will talk about each one of these issues, how it does. It is very complicated now. Sometimes when I see some people actually doing scheduling on cloud computing, first come, first serve scheduling, I actually say what they're doing. Cloud computing, first come, first serve scheduling. We did this in 1970s, first come, first serve scheduling. We don't do it. I never heard. Sometimes I don't know. I get papers to review with first come, first serve scheduling on cloud, where we know now cloud is dynamic and workload change. People stop, add, increase, and so forth. And in particular now you actually also can demand. And the service provider can say, okay, if I don't give it to you within 2 hours, you don't pay. So that is a loss to service provider. So the scheduler, the resource management and scheduling now has to work hard. So the resource management gets paid. If it does its job properly, it gets paid. If it loses, then the owner loses. Okay. Most of these I'll talk about it later on. Now we have different types of cloud computing, private, hybrid, and public cloud computing. Really, we can break down the cloud computing offerings into infrastructure, platform, and software. Okay, so if it is private cloud, you actually host it on your own business location. Okay, so everything that you see here, you are responsible to manage it. You are responsible for the application. You are responsible for runtime, security, the software, and virtualization, and servers, storage, network. There are other resources that I didn't mention here. So this is basically a cloud, but you are responsible to manage. And then we have what is called public cloud. Now in public cloud, see all these infrastructures that you see here, you rent only. You rent the servers, you rent the storage, but you are actually own and run your own software. This is called infrastructure as a service. The vendor that you buy, you rent from, is responsible to manage the infrastructure. You are responsible to manage the rest of the resources. Now, the reason I actually split these ways is because I want eventually, when we come in the couple of days, the resource management is actually responsible, which part of this is responsible for. We can't write dynamic resource management and scheduling simply because of cloud. We need to know which part of these resources I am renting. So for this, it's not that big deal, right? Because I am managing only. And the workloads that come to this cloud, basically known, is an organization is running these workloads for many, many years. Maybe new ones can come, but you can actually write a scheduling algorithm that does very good job. But the workload on here is different because it comes from different people. The web services, the MapReduce, the workflow applications, all these can come. Different heterogeneous applications can come on these resources. So your scheduling, resource provisioning and management is different, right? So you need to actually know how these are prepared to optimize this part. If you don't know this part, you can't optimize the other part. Okay? Now, then it is what is called PaaS, which is platform as a service, where in this case, you actually not only rent the infrastructure, you also rent the platform as well, the databases, the other, like what you call SaaS, in all these platforms. You can actually rent and use them, but you write your own application. So you manage this, and the vendor will manage this for you. Okay? The last one is actually where you do everything. Okay. Here's I'm going to rent the application, the platform, and the infrastructure, all. Now, this, for me, I call this public cloud, because everything is there. I call this not really a public cloud, because most of it, the owner controls it. It's only the infrastructure that the cloud service provider controls, right? So if you actually developing quality of service or service level agreement, you really need to know if this one is more serious, because you take the entire responsibility as service provider. Maybe you really specialize in infrastructure, you subcontract the platform, and then you subcontract the software, right? So no company actually have all of this. Yes, Microsoft is someone that has all this, but never this part. There must be a subcontract in here. So your service level agreement is more complicated than actually a simple one that we still design for this and we use it for this. I have been saying this is impossible and show me if it works for this. It doesn't. Why? Because this involves subcontracting. Where this one, I can use Amazon's entire server. And I can use SQL from Microsoft. Who is going to talk between these two? Me? If it is here, I'm just saying here, all I want is the output. I don't care how you guys doing it. You do it. So one contractor will take it, subcontract it, and return the thing for me. Now, if I have to negotiate, so I will negotiate with this person will negotiate with them, and every one of these wants to make money. So they also have their different service level agreement. This problem has not been solved. No one read a paper and bring it to me. No one actually talk about this. All service level agreement is done for this. Yes, we can do it for this. We can also do it for this, even though much more harder, complicated than this. But this one, the true public cloud, is very, very complicated until and unless we have one resource provider that provides everything. The infrastructure, the platform, the software, at the same time. And nowadays we are talking about disaster recovery as a service, data center as a service, fault tolerance as a service. All this, what this shows is that the cloud is getting more complicated and complicated. Dynamic provisioning, they used to call NP hard, NP complete. It's actually now becoming even harder and harder. Okay? So, now, not only service level agreement, scheduling becomes very, very difficult. When people say, I'm developing scheduling on cloud computing, and they're only doing 2 tasks. I have seen people actually submitting 2 tasks to cloud and say, I'm doing research on cloud computing, impossible 2 tasks. My laptop can run actually 20,000 workflows in few minutes. How come you use the cloud for 2, 3 tasks, 10 tasks? Impossible. So scheduling is very difficult. If you're looking at this, we always remain within this area, infrastructure, scheduling for infrastructure only. Fault tolerance becomes very serious issue. I'll talk about it. Energy becomes very issue. Quality of service becomes very issue. And all of this also depend on the application, the workload type. Okay, so what we talked about, I simply said about public and private cloud without actually telling you exactly what they are. The public cloud, everything is actually provided by third party. So this is the idea. As I told you, that definition for me, at least for me, it doesn't work. Because third party can provide this part, third party can provide this part, and third party can provide all of it. So unless we actually make clear what is provided in here, we can't really say third party. So there is hybrid cloud and private cloud. You can't see that cloud here, right? Can you? They are clouds, these are clouds. So private cloud is basically a locked down, only used by owners, if you link these two, you get what's called hybrid cloud. But hybrid cloud, basically, you have your own private cloud. When you need more resources, sometimes when resources become, remember earlier I said resources fluctuates up and down. When your resources actually, when your resource need is more than private cloud, then you can actually send some of them to public cloud. So you buy resources from public cloud instead of buying and adding resources to your own data center. That is the idea of hybrid cloud. It's a mixed usage of private and public clouds, only leasing public cloud service when private cloud capacity is insufficient to do the job at hand. Again, here becomes an issue. Which job you actually send to public? How do you decide? See, the private cloud scheduling before was interesting, but now becomes even more interesting because you need to make sure which job you're sending. Is it the largest job or 3-4 smaller job? Is it sensitive job or insensitive job? What if all of them are sensitive? How can you do it? How can you leave data here and run the process there? It becomes now very, very interesting in hybrid cloud when you perform the scheduling again or resource management. Now, we still talking about cloud, but the application types that we run on cloud have changed. As you can see, these are new applications, completely different. We did not think about these applications earlier. And these applications include smartphones, tablets, and wearables. And we talk about smart cities, smart TVs, smart fridge, smart cars. All these applications will use cloud computing. And so, as I said earlier, it's in excess of 50 billion devices are expected to hit the cloud in a couple of years. And so, because cloud tends to be one big data center, it will not actually be able to handle this increase. Moreover, these applications are different. Scientific applications are very large. See, if you look at weather crunching application, they have some threshold. You know, they can tolerate 5-10 minutes, an hour, in some cases, delays. But these applications don't tolerate. The latency tolerance is very, very small. Okay? So, what happened? We came up with something called fog computing. Now, fog computing is basically based on, at the center is based on cloud computing. Okay? Now, this at the end, what you see is different types of applications. Sensors generate a lot of data. And this data is going to cloud, as is now, right? So sensors generate data, we store it in cloud and process it. The same, smart cars, smartphones, and all of this do actually produce data and send it to cloud for processing. Now, what the problem with these devices are energy hungry, right? Energy. They don't have enough energy. They can die quickly. Their processing capacity is very small. They can't process a lot. So what do? The data they send from here to there takes long time. The concept of cloud computing is, why don't we use, there are nodes such as routers, mobile base stations, switches, and so forth between cloud, data center, and these application producers. Why don't we use them to process this data? Why don't they do actually some tasks? You can send small tasks to them. They can process that, right? Send the result to cloud and then do that, continue. That is the concept of fog computing in a nutshell. So the whole idea is take the load, if you look at it from there outside, take the load of storage and processing from the cloud to where? To the edge nodes. These could be routers, these could be laptops sitting there. So it could be you are using your mobile phone, right? Instead of doing processing on your mobile phone, it will go to your laptop, because laptop has more energy, more processing capacity, more storage capacity, and it will go there. Now, if you take a lot of photos on your mobile, your battery drains quickly every day. Because keeping them up takes a lot of battery, right? So if you store them on your laptop, because it has more storage there, you increase your battery on your mobile phone. And if you do some processing, you can also pass it on to your laptop, which actually can do that. Instead of actually sending it now, when we read email, we read it where, right? Gmail goes straight to cloud, get the data, and come. Right? So why don't we do it on my laptop? So the whole idea of fog computing in a nutshell is this. It's more complicated than this, but I'm just giving you an idea. If you want to read more, this is the latest paper we publish in this area.
Professor Jemal, some of the papers have even differentiated between the fog computing and the edge computing.
Yes.
They say that the fog is like router, switches, etc., and the edge is the device itself.
Yes, that's what we do actually here. We did this here. So we started here. Many people talk about this. So we did actually say yes. In fact, we went and proposed a different, based on what Professor DP said. We proposed a new model, and this new model it appeared in which is this one? Yeah, in Access. This is the new one. So what we're saying is this: actually, we combine fog computing and Internet of Everything, particularly for big data processing, because most of these small devices generate a lot of data. Internet of Things generate a lot of data, and we propose this idea of actually putting fog data service in between cloud and the edge fog nodes, and handle all these volume, variety, and velocity of big data characteristics. Okay? Yes, we do actually, if you look at this, we put them out. We do acknowledge fog computing routers, and they are different than other nodes like laptops and other things that exist in there. For example, base station, mobile base station is different. That's good point. Now,
another big issue is to decide on, when, let's say you are performing the scheduling operation,
yeah,
to decide on which computing, let's say, should go to the fog and which should go to the cloud.
this is another level of complexities. So every time you come up with different platform, you add another level of complexities. Like Professor DP said, should I actually schedule here? If I do, which one of these nodes? Or should I actually go straight to cloud? And if I do, what are the latencies? The application is the one that determines actually right now. Also, the scheduler has to be very careful because of these guys themselves better than these guys, but resource-wise, but they are also limited. They are also exposed. They also can fail, right, if you overload them. So a lot of, when we added another layer of scheduling complexity, as Professor DP said, in fact, that's the area now we are working on. There is a problem in terms of scheduling here. Another thing that we also found is we do actually reduce a lot of power from cloud, but because we're using this, there is a problem called wear and tear. Okay, a lot, because you're using them a lot, they start failing. Okay, so because you know you have to configure them to use them, right? You configure them certain ways. And this configuration is handling only certain types of messages, if you keep sending different messages, it can also reject a lot of jobs as well. This is another work that, as I explained it, particularly to handle the big data issue that we published this year. Now, the whole idea of cloud computing is really the virtualization technology, and it basically gives you a perception of single physical machine, and it also enables different types of operating systems to run on, so you don't care about heterogeneity now, because you only look at the virtual machines, separating applications from the underlying infrastructure. So you don't actually worry about here, because the VMs are going to run, encapsulate your applications, and also it ensures portability of VMs between physical machines, in particular when you want to do VM migrations to increase the utilization level or to decrease energy. And you can consolidate these virtual machines on smaller machines and shut off the unused ones. Now, this is another virtual data center, which is basically mimics the resources here. Okay, this is the idea of now data center as a service. We virtualize the data center as a service. You can see virtual data center here. You can see virtual data center 2 here. The physical resources remain the same, but we can now, instead of actually renting virtual machines as we do now, we can actually rent now the data center itself. This is the idea of virtual data centers. Okay, let me go into workload types that are now run in some of cloud computing. We divide workload types as divisible and indivisible workloads. An example of divisible workload is matrix multiplication, where you have tasks can be actually, you can divide this into task 1, task 2, task 3, this application, and then this application will run on individual nodes. Okay, so you can then, now the only thing is that these tasks have to wait for this one to complete, right? So in fact, you can schedule these two together, task 1 and task 2, or task 1 and task 3, and task 1 and task 2 together, and then these two has to run separately. So all you need is 3 virtual machines. Or you can, if you actually run all of them together, or there is this one actually also sends the output to this one sends the output to that becomes an indivisible workload, because now you can't actually divide them. They all have to run on the same machine. That actually makes scheduling very, very hard. Okay? So at the top, we can actually divide workload always as divisible and indivisible. But it's more than that. There are some workloads, workflow applications, for example. You can see this workflow application, which is very, very common nowadays. There are, this works, this T1 can be actually run first, and these two can run in parallel, and these two can run in parallel as well, because they only depend on this, and these two can run in parallel, and then this waits, this runs at the last time. So the scheduler in workflow application usually looks the longest path, right? So that is the time, the most time it takes. That is actually not true. If all the tasks have the same runtime, and if all the networks are 100% dedicated to send this data, that is true. But because they may have different running time, or maybe they are sharing the resources, and they are sharing also the network, maybe this is actually scheduled on a machine in China, and this has to send that data to this guy. It takes much more than actually just looking at the longest path. The latest one, which is really this one, but in a different way, all you have is 2 tasks. What is called map and reduce, which is actually became very famous nowadays. There are only 2 tasks, but the mappers can be multiple of them. You can have multiple mappers, and you can also have multiple reducers. And this can actually have another level here. You can keep going. So what basically mappers do is these mappers always have to run before the reducers. That's the only constraint. And the mappers will actually take the data, break it into smaller tasks, and return what we call key value pair. So it's like a dictionary. If you know Java or you know Python, it's a dictionary which has value and key. And that returns goes to the reducers, which actually collects those data, those results, aggregate them together, and outputs it. Okay, so now we actually work in this area to make sure that they properly scheduled, because if there is a sync, there is no sync between these two, a delay that is introduced can cause service level agreement to be violated. And you need to make sure that there is a sync when you schedule, map, and reduce together. These are the table of cloud workload types. Most of cloud workload types are web services nowadays. Okay, so this is the most widely used, and then followed by scientific workflow type workloads. A lot of enterprise software, lots of applications from software, and testing also is done. The second one is called client-centric applications, such as productivity applications, graphics, and so forth. And then mobile-centric applications, which is basically Twitter's, Facebook type of things, and so forth. Again, this is basically what cloud will give you in terms of growing faster if you actually have applications that oscillates, right? So sometimes some applications have scientific applications in particular. What they do is that you take 10 tasks, you run them just to produce the result. If the result is okay, then you keep with another 200. So it keep increasing. Most of these scientific applications that used to be run for a month, 2 months. Now that's the strategy we use. You run first a small one, and if there is a bug, you correct, and then you run until you see the results look, and then you increase the number. So it goes up and down, it grows. So this kind of applications is very good for cloud. And also the peak is sudden peak with performance, and also seasonal trends. Again, most of it is when the fluctuation occurs. This is again with MapReduce, which I already talked. This slide is supposed to be before this slide. Forget about market-oriented cloud, but the cloud architecture, this cloud architecture, we actually developed it in 2012. And we still use this. The first paper we published with Raj Kumar and a PhD student. So I use this on my slide. Raj Kumar also uses it on his slide. He always puts market-oriented. I use dynamic cloud architectures. My work is in a dynamic area. His work is in market-oriented area. But we work together very, very well. So what basically this slide summarizes what cloud computing is all about. At the bottom, you have physical machines, and in between here, you have virtual machines. These virtual machines are allocated to the physical machines. It's not your application, it's not your tasks. When somebody says task scheduling on cloud computing, that's not actually true. It is the virtual machines that gets scheduled on the physical machines. And each virtual machine can have one or more tasks. So in this case, these two virtual machines are mapped to one machine. So what this allows us is that if we find this machine is actually overworking, or we don't need this machine, but we can move these two virtual machines to this machine, and then we can shut this machine off to save energy. So this idea of virtualization is very good in terms of consolidating virtual machines. And also they're good because we don't worry now about different operating systems. Your application needs maybe Windows or Linux or whatever. This actually can handle all those heterogeneities. But these ones are actually managed by virtual machine manager here, sitting somewhere here, and monitored. We also have pricing. Again, there is a number of different pricing. I'll talk about this when we get to that in a couple of days, or tomorrow or the day after. It depends on demand and supply, right? So some providers simply use a flat fee. Some providers use what's called spot pricing. I'll talk about all those things when we get there. Accounting component is needed because you have to pay for what you used, right? It's just like metering. And monitoring service requests to ensure that service level agreement is met. This one dispatches applications that are accepted. We build a lot. This is not new, but we build a lot on these structures. Like we have now what is called a system that actually checks. I forgot its name. That checks whether admission control. So whether a new request can be admitted or no based on the service level agreements that we have. And if we actually can admit a job, we must make sure that the service level agreement is met, both the previous ones or the other ones. And I actually now work in something called double scheduling, where I can actually basically kick the low service level agreement, low priority jobs, and put the high priority jobs. So what I'm saying is that if I get someone, customer who always comes back and gives me, buys from me $20,000, $15,000 of resource, $10,000, $5,000, almost on a daily basis, if somebody who occasionally or just came in and using 3, 4, I can violate the service level agreement of that guy in order to keep this guy. I'm not kicking him off, but I'm just violating his service level agreement a little bit, to the point where I finish, I'll just tell him, free for you. So he won't be, he or she won't be angry. I'll give it to him free, based on the work I'm doing. Or I will charge him 10%, 50%, whatever. So we found that most of these people, non-regular users, are very happy even if you give them 5%. So you explore that psychology, but these guys are very hard. Once you lose them, they don't come back. The ones, regular ones, they really need the resources, and they need it now, not later. So I am actually using that dynamic, that admission system as a dynamic admission that works with service level agreement to make sure, so before scheduling, they can say A, B, C, D are possible targets. Okay, and so you don't go and do it while they are running, but you just say these are possible targets that can be delayed, and then reimbursed the owners. That's where service level agreement, resource allocator is sitting, and on the top you see a lot of users with a lot of different applications, and in between the users and the resources is what we call brokers that actually negotiate service level agreements, quality of services, and so forth with the end users. I think that's all. Yeah. Thank you very much. I'll be happy to entertain as many questions as you want.
What is the difference between QS and SLA?
Okay, service level agreement is basically when you get your mobile phone. What is it called? Aritel now? What is it in India? Airtel.
There are many service providers. Airtel is one of them.
Airtel. I'll just give you the simple one. So really, even though when you said, when they give you this service level agreement, you didn't read, you just click it and say, yes, I agree with it. This is what most people do. But if you read in there, and then you go back to them, and you say, no. If I go in the lift, in elevator, and my phone cut off, if I lose any money, you pay. Because I'm making a business call. So service level agreement is that the agreement the service provider and the client make. So you provide me this service, this I want this to be finished by 5 p.m. If you don't finish by 5 p.m., there is penalty. Okay? That is the agreement we make between the provider and the service user. Okay, service level agreement, okay? Quality of service is when you want the quality that you expect. Okay? So if the service provider says, I will make sure that your data, your result, will be exactly what's computed. We are not going to fudge it, to change it, but the quality will be provided to you. Okay, if I'm a doctor, I will provide you the quality healthcare to you. That is a service. That's quality of service. But the service level agreement is that you're paying this much. Okay, if you're paying 20,000 lakh, I'll give you private jet where I will operate you in there. If you're paying 20 rupees, I'll take you to somewhere under the bridge, I will operate on you. That is the deal on service level agreement. That's the difference between quality of service and service level agreement. Yes?
What is the difference between federated cloud and hybrid cloud?
Hybrid cloud and?
Federated.
Oh, they're the same. So, I think I'm the one most of the time who call it federated, and I rarely call it hybrid. But anything you federate means you connect two things or three things. Federated cloud and hybrid cloud are the same.
So what is the virtualization of data centers? I mean, how do we do that? The virtualization of the system, servers, and the data centers?
We actually now, before we virtualize only CPUs, we actually now virtualize the network also, virtual networks, what we call software-based networking. Now you have software, the networking is virtualized, the processors are virtualized. So by virtualizing these two, you automatically actually virtualizing almost everything that's in the data center. And so you partitioning the data center along this virtual network and virtual server CPUs. That's basically what you do. But you do it in a hierarchical fashion, okay?
So you talked about the total public cloud, and in that you talked about that service level agreement is really very tough in that if you are having multiple agencies involved. So as a customer, what is my role? My role is to have SLA with the main dealer who is dealing with me. I am not concerned with the interior. So how to look at that particular aspect?
Yeah, that's a good question. It's not the user that complicates the SLA for pure public cloud. It is the inter-service providers SLA. So if I say to you, I will provide this service with this quality as by this amount. Now, if we actually, this particular person goes and subcontracts 2 or 3 service providers, what happens if one of them did not provide the service quality that is promised to you? Because your whole application will delay, right? So that complicates the whole issue. It's not between client and the only one you deal with. No, it is actually between the service providers that complicates it. Because every one of them, they want to make money. And it's better for me to actually directly deal with the client, even though this service provider becomes my client now. But if I can actually talk to the client directly, it is easier. As I told you earlier, if you are low customer, then I can actually always give some delays and give it to you for free. But if now the person who came to me now is actually subcontracting this to me, this person may be subcontracting 20,000 of such small jobs, still a big money for me. So it becomes very difficult for me which one of these tasks now I can actually delay. Any delay, he will be accused of. And the client will always accuse, not happy with this main guy. And the main guy now can't actually delay anything. But in any systems, delay is unavoidable. Whether you do it intentionally or unintentionally, when you share the resources, you try to maximize the output and minimize the cost. But when you do this, these are 2 conflicting criteria. So you just need to get the balance right, knowing that sometimes this balance cannot actually be, cannot align together. So one will go up, one will go down. But when you have multiple service providers involved, this balance becomes even hard. That's why I'm saying that it's very, very difficult to develop service level agreement when you have multiple service providers negotiating each of them is specialized in certain areas, right? So the software provider specializes in software, hardware provider specializes in hardware. We know that most of the time hardware is actually easy to develop service level agreement for. Software always not easy, and combine these 2 together now becomes a bit harder.
Sir, nowadays, Amazon has the biggest market share in terms of cloud computing. So now Azure is also lining up for the competition. So is there any specific difference between Azure and this Amazon Web Services, AWS?
This is one question nobody can answer except the people in Amazon, because we don't really know. We know that Amazon has these many servers, but how they do things is really, for me, if you ask me, I don't know. I can tell you I don't know. Which one is better? That depends on the application and service level agreement that you wanted.
Like we have seen that Amazon uses most of their services in Linux, and we don't have any Windows-based servers for these cloud-based services. So I just want to know if Azure is launching some Windows-based services for that. I'm not sure.
As I told you, these people don't tell you. They can actually say, we don't run this, we run this, we run this. It's a really well-kept secret about their data center, their resources. We estimate now, I can estimate how many servers they have from attending their talks. But this is just guesstimate. It's not actually even estimate. We don't even know how many servers they run. We know that they have data center in India, in China, in US, in one in Australia, but we don't even know what is in there. How many? You don't even know how many people work for them. If you ask me about Infosys, I know better than Azure. I seriously don't know what they have, what they run. I use their resources. I don't know how they run their costs, their resources. Because if they open this, they open themselves to competition, right? And to hackers as well. So
even how they decide about the VM provisioning and the cost is decided.
We don't know. No, very little. So we really don't know, because these are very well kept secrets. You go there and you talk to them. Sometimes, some in a healthcare environment, if you run healthcare applications, the HIPAA, for example, says you must make sure that your data is backed up, your data is safe, your data is this. But when these doctors or healthcare service providers go and say, we want to purchase a service from you, but these are our requirements, show us how you achieve this, which I personally seen this, and they refuse. We're not going to tell you how we do the backup, or we're not going to tell you how we do the disaster recovery. So if you want to buy, we will guarantee you these services, but we're not going to tell you. Even though the legislation says for the health providers, you must know how you do it, because they send auditors. And these auditors come in and then they have to approve. If you don't have what the cloud service providers do, how do they approve? That's why many of these applications are not yet moving to cloud.
So this brings me to one question, since every cloud provider has conflicting interests, it's a business model, so everyone is focused on making money for themselves, not for others. So federation of cloud, if we talk about, will it really work?
That's what he was asking actually. That's federation of clouds is basically when you use private and public, and you federate together, or you can actually federate. I never thought about this. You can federate to private clouds also if you want to, but nobody talks about this. That's why I don't talk about much. Well, if you see my slides, I put key in the private cloud, so it's locked down. But you can remove that key and put two. In fact, two private clouds make better federation than private cloud with public cloud. Because with public cloud, which one you choose? Because these guys are conflicting interests. And they also put you in lock-in. Once you agree with them, you can't get out of it. It's just like you are locked for 24-hour month mobile phone. For 4 months, you have to stay with this service provider. That's another issue. But if two private clouds work together, they actually can make a better federation, according to me, because they're not after money, they are after resources. These ones, the business model is to make money, to make more money. So, do they work? So far, they seem to be working because they're not providing the same thing. Because, some of them, they will never work together. If you take Microsoft, Azure will not actually make a service level agreement with Amazon. Right? Because they're in conflict. But if you take private cloud, which doesn't deal with any one of them, but chooses based on their money and their interest, they can rent some of the resources from any one of them. The idea was that. But when you bring in any selling and purchasing, it is always affected by psychology. The psychology that they play on consumers, they also use it also on the organizations as well. So the question you raised, we don't provide, they don't provide Windows, we provide Linux, and we provide that. All this is actually more of a psychological issue because virtualization will allow you to run your application anywhere. But when they saying this, if the user doesn't know that they can run their application anywhere, they will say, oh, okay, this company doesn't provide what I want, I'll go with this. This is more of the issue. So I seen it work, but I actually prefer if two non-competing organizations, private clouds, say like two universities, we always have a small data center, every university has. They can easily share their resources rather than actually go out and buy from Amazon. They can form federation of clouds. We did this before. If you remember, we did federation of clusters. We call multi-cluster computing. Successfully, grids actually happened on that level successfully because money was not involved. It was actually done on goodwills. So private clouds have, if based on goodwills, federation can work much perfectly than actually now working with one of these service providers. This is my belief.
Sir, but even now Google support the federation by 2015 and Amazon now support the federation in 2017. Even we have storage in Amazon and we have application in Google.
Yeah, no, what we say is that, but you see in business follows the demand. If the users demand, they either survive and provide what the users want, or they perish. This is what the business model is. What Google is doing is actually following this trend. It's not because they wanted to. They can actually provide this, and Amazon also has to provide this. But this is on the smaller scale. What we are talking about is that the hybrid cloud, where you can say, look, I want to buy 10 machines from you, 20 machines from him, and 20 machines from him, so virtual machines. We can have, if he gives me 30% discount, you give me 20% discount, you give me 10% discount, why can't I actually link you all together? But that is never happened. That is where we're talking about hybrid cloud now. That will not happen because that brings competition, conflict, right? Did you understand what I'm saying? Okay.
Sir, what is soft level objective? Does it mean quality of service? If it is no, then what is the difference between quality of service, soft level objective with software level agreement?
Soft level objective?
Yes. Soft level.
SLO?
Yes, SLO.
I think he is asking because in SLA there are two types,
Yes.
soft and hard.
Yes.
hard it has to be meet. Then usually when we model the program, it should be as constraint. But when it's soft, then it can be violated, but the provider has to pay penalty. Then usually we put it in objective and we try to minimize it. That's the difference between soft SLA and hard SLA.
No, we actually do this in real time, hard real time and soft real time.
Actually, what is the question that you can repeat?
Yes, sir. Soft level objective.
No, soft level objective.
Yes. SLO. Usually we read as a SLO.
Maybe some objectives are achievable, some are not achievable, or something like that.
No, I am trying to remember what he says. There is
soft level objectives.
Sir, it is service level.
No, yeah.
It's not soft.
Yeah, service level, yeah. But service level, you see, we only have SLO is something different. But I know what it stands for, but it's not service level agreement. In real time, we say hard real time and soft real time. But that is quality of service, not service level agreement. Service level agreement is you make an agreement, okay, and usually we say when we do agreement, plus or minus 3%. So we will violate 3%, or you will give you 3%. This we know you give me some level to play with, because when I provide you service, there is some probability that I can't actually maybe achieve, the system will fail, or there is the delay because of the network is busy. So usually when we make an agreement, we put some, if I can give you 3% earlier, your result, or I can delay 3%. But we don't have actually where we say it is either you give me, you don't give me, or you can do lower or higher, unless it is real-time applications. Real-time applications have constraint, hard real-time, soft real-time. Okay?
So any other questions if you have?
I'm happy to answer if you have any questions.
If you have any other questions, because it is just an introductory cloud computing talk, and I hope that of course you are all aware of the cloud computing. It's a recent emerging kind of a discipline, and the whole lot of work is being done by Professor Jemal itself, as you know. So it's good that you had some better interactive session, and you could ask so many questions with Professor Jemal. I hope that in the time to come he will satisfy, and at the end of the day, maybe after 2 weeks or so, you'll be able to do some actual research in the resource provisioning in cloud computing, which is really a tough topic and becoming more tough because of the invention of the IoTs and a whole lot of IoT, the data being generated by the IoT devices. So, very nice, Professor Jemal, thank you very much. Maybe after lunch we'll have a kind of a some demonstration, tutorial kind of a thing. Probably you can interact more in that. That will be a better opportunity for you to. So we can have our small lunch here arranged, and then later you can join after an hour or so here at the same place. Thank you very much.
This practice afternoon class, one is using Aneka or using Cloud SIM. So, do you all have laptop?
Yes, sir.
So all installed Cloud SIM in Aneka?
No, I will not.
No?
Cloud SIM.
Okay, so we need to install, then this doesn't make sense. I think we need to install Aneka, and then we can actually give you the work to implement, and then we can discuss and do that way. But I'll just go over about Aneka.
What they should do? I mean, they should install Aneka. It's not a free version.
Aneka, they can access the free part. We can do it on Cloud SIM.
If you display the link where they can install Aneka,
Yeah.
probably they can, because we have the Wi-Fi here and they can through the GNU Wi-Fi. They can download this particular one and can install it.
Okay. Let me try if I can install it. Then you should be able to install it.
See, one thing is there that you can use the Wi-Fi. GNU Wi-Fi is available here, right? The ID and password will be provided to you by Kishan.
Yes, sir.
So Kishan will provide you the ID and the password. All of you can use that. GNU Wi-Fi can download the Aneka. Can download even the Cloud SIM also. Cloud SIM is a freeware.
Yeah, both
Right?
actually
So
download.
download both at your laptop, and then you can use it. The tutorial work
Yeah.
which is being given here.
Yeah.
So you can use those.
Download Cloud first, Cloud SIM, and then we can work on that.
JNU Academy से कनेक्ट करना था ना JNU Academy.
Aneka doesn't allow you the whole version.
Username and password.
सबको बता दीजिए, यहाँ डिस्प्ले कर दीजिए. Just use this laptop and then just display the ID and the password. ID password बता दीजिए. So all of you can log in on JNU Academy. The network is JNU Academy. You open it, you will get the firewall. You can log in through this. That will appear itself.
Yeah, that's just the password.
So on this particular JNU academic link, right, you just use this user ID and the password. You can log into the JNU Wi-Fi.
What is it?
Yes. Yes,
Just give the link of Aneka.
Yeah.
Link straightforward to download the Aneka.
Yeah. Good there. Just take this out.
Gas 23.
No, let me see.
कनेक्ट हो गया क्या हो गया गैस अंदर
No.
जी कैप्टन
हमारे वहाँ भी होने को थे ज्ञान का कोर्स, तो वो इसी पर ही कराते हैं ज्ञान कोर्स है। तो वहाँ पर हमने दिया था प्रपोजल, राजकुमार भैया सर भी करते हैं, तो वो भी इसी पे करा देंगे। तो वो एक्सेप्ट नहीं किया।
Yeah.
जी कहते हैं अभी तक नहीं हुआ ना।
I think you have to register to download Aneka first, okay? To get the free copy.
बैटरी रात में लगाना चाहिए। 35 पेनड्राइव मिलेगी। सॉफ्टवेयर है मेरे उसमें डेस्कटॉप पर डिपार्टमेंट में। अभी हाँ यहाँ पे करिए, यहाँ पे करिए, यहाँ पे करिए। अभी आपसे पूछेगा रजिस्ट्रेशन नाम डाल दीजिए अपना एप्लीकेशन तो मिल जाएगी। तो वो लेते ना मार्क करके तक मैंने काम किया।
Yes, yes. See. This is.
की रिकॉर्डिंग हो रही होगी तो आप लोग गए होंगे, ऐसी रिकॉर्डिंग हो रही होगी तो बोला कि अपलोड करके
Okay, so we actually use Cloud SIM today because this is our first day. We will basically do a very small modeling of workload. So what we want to do is we actually want to model a particular job, not really a particular, but as we go, this will become more complicated. Every job that arrives into the system have at least three requirements. Number of virtual machines this job needs, and the arrival time of this job, and how much time it needs. So these are the main modeling. So if you don't have real applications, you want to model the applications. So we can model any applications by using at least these three. There is also, if you actually wanted to go and model workflow applications or the matrix multiplication application I showed you, you can also use this. But what you do is that the service demand is for the entire application. When you break it into different tasks, if you want to make these tasks homogeneous, you just divide the time among the numbers of the tasks. If your job requires 3 virtual machines, let's say, and the job needs 9 minutes to complete, each task will have 3 minutes. If you want some tasks should take more, then you can actually use a number between 0 and 9 and then randomly assign. Then this number has to add to 9. The total tasks, the total number you assign randomly, one can take 5 minutes, the other can take 2 minutes, 7, the other can take 2 minutes. One can take 4 minutes, the other can take 3, the other can take. If you want that they are not equal, this is real case. So this is how we model applications. When we divide them, this is how we divide. If we want them, they all do the same thing, equal amount, we give them equal amount. If we believe that they do different amount, then we actually assign them accordingly. All tasks will have the same arrival time because the job arrived at the same time, and then the job is partitioned into different tasks. Usually we use random. We assign the virtual machine the number of virtual machines you need randomly. But tomorrow I will show you, or we'll talk about how we can actually assign choose. You see, there are now small, medium, or large. So we want to actually also use, similar to service demand, how we partition the time. We can also select for each task, whether or for the job, one big or one small virtual machines. Again, the arrival time for all of them is the same. It is only as the scheduler uses the arrival time to discriminate between different jobs. Now, how do we do? How do we actually model? Most of the time, as I said, VM is randomly, you can choose. The arrival time is we use Bayesian distributions. This is really approximates the arrival of jobs into the queue, into the system. A lot of people use this. I use this most of the time. So what we're going to do today is not just, we first create just for one, we model one job, but really what we want to do is we want to submit a lot of jobs. So we loop and create a lot of them, and you will see that some of them arrive. You need to actually do start time from 0 and then increment. But you will see that some of them will arrive at different times. So if you get some value, you start 0 plus that value, horizon distribution that you got. That is the first arrival. The second arrival will be plus of what the time now you have. So it increments like this. This is how we model job arrivals into the queue or into the system. Now this gives a nice opportunity for each job. Sometimes you'll see they may have very small, or in fact close to one another, because you're generating a distribution, right? Sometimes you get big gaps, sometimes very small. And the second one, if we can start with arrival time modeling, and then we do the virtual machine, the number of virtual machine, and then we'll do the service demand. Okay? Anybody knows the formula for Poisson? Job A, arrival equal to what? Yeah, so minus lambda is what? Rate, huh? Arrival rate? Yeah. Yeah, that's correct. So we need to write a Java program within Aneka or CloudSim to actually just simulate this. Just write one job for one job, and then we do it for 3, and then we go and also do virtual machines. So the virtual machines, for now, we simply say this job will need any number from 0 to 10 virtual machines. Every job, so we wanted to randomly select between 0 to 10. For now, let us assume all the virtual machines are equal, okay? Not small size or large, but equal size. It will just tell us how many virtual machines we assign to this job. And then accordingly, we break the job into a number of virtual machines. Okay? You want to do that? Yeah. Or no? No? Okay. This is really what you need to do. If particularly you're doing research, you model first, and then once you model, you start, if you get the real applications, or you get the trace, and then you can see where the graph should actually match, at least come close to each other. You can't, I have seen a lot of people simply saying, I'm scheduling, and then they randomly assign tasks 0.7 minutes, 2 minutes, 1 minute. You don't do like that. We actually assign arrival rate using a particular distribution. We are modeling these particular tasks or jobs. We just don't get a number from anywhere. And you can easily justify, because many people do actually use these modeling techniques when they represent the jobs, right? You can say so-and-so is using this model to this approach to model their jobs, and easy to say, instead of I got this from some of dream numbers or put together. So I'll go around, try to help you if you need. If you want, you can also write it in Python, if you feel Python is easier. Or if you don't know any both of them, then I have to write it. I actually have all of this in my laptop, but my laptop went to sleep. So until it wakes up. But the Java program is not even, very small number of code, not even 5 lines or 10 lines. Anyone wants to take a crack at it? No? You guys work together. Oh, it's not working for you? No? But you can actually do it by hand. You don't have to write a program. So the formula is just job is equal to a job is equal to e to the power of lambda t. Lambda is arrival rate. Yeah, this is current time. And this is arrival rate. So you give a rate, constant rate. So this stays the same, but this changes. Yeah. So you start with start whatever you give value. Okay. You say this job 1, and current time. This one, and this one you give the value whatever you want, and this remains constant. And job 2 will have, you repeat this, but now this changes, right? This remains, this change. The time changes. So, yeah, I just do it for 10. Just do it by hand. You don't have to do it. Yeah, this is the formula. This is the start. You can use, see, I was using my current time. Fix my data. Okay, so for job 1,
is arrival rate.
Arrival rate.
Okay.
So you can do this for job 1, and this will now T will change, right? T is T before, this 0, right? And then the arrival time of this plus whatever time now. Okay, T1, and then job 2 is lambda into T1. What's this? Something like this. This is 1, this is 2, this is 0. And go like this. Okay, do it for 10.
This is G.
Guys, you can do it by hand. Just this job.
G1. This is E is epsilon e to the power f plus 2 e के minus lambda plus into T naught
P1 है नेक्स्ट जो टास्क होगा उसका क्या टाइमिंग होगा
T plus T0
तो जब जॉब 2 के लिए तब उसका टाइमिंग क्या
T1 का तो T0 के इक्वल होगा ना
T प्लस T1
T स्टार्ट टाइम है ना
ये स्टार्ट टाइम T नॉट हो गया और T1 इसकी जो वैल्यू आएगी यहाँ
T1 तो आई थिंक T नॉट ही होगा पहली जॉब का जो टाइम होगा वो T नॉट ही होगा तो नेक्स्ट टाइम आएगा उसमें T नॉट प्लस T करेंगे है ना
इसका मतलब टाइम में लैम्डा है
जॉब 2 है
जॉब हाँ इस तरह चलते जाएगा जॉब 2 हो जॉब
टाइम पे चलेगा ना सर जॉब 3 हुआ ना ये जो माइनस लैम्डा T2 आएगा यहाँ
सही है
लूप चला दिया अब आप ये कर लीजिए T1 वो एक एरे लेनी पड़ेगी
इसमें लूप लेना पड़ेगा लूप लिया
एरे लेनी पड़ेगी ना
T10 का एरे लेवल T10 प्रिंट करवा देंगे कैलकुलेट करना पहले ये कैलकुलेट कर टाइम आया जॉब आप T10 एक ले लो ना every 10 seconds 10 seconds
एक्सक्यूज मी निकल लिया इसको उन्होंने कोड लिखने का बोला है कोड ही लिखा है अच्छा सब कोड लिखा है
E की वैल्यू तो क्या एक्सपोनेंशियल 2.71 है 2.71 है इक्वल टू 2.71 एक और वेरिएबल
हाँ एक टेम्परेरी वेरिएबल लेना पड़ेगा तो उसकी वैल्यू चेंज होती रहेगी
पूरे मेरा क्या होता है एक्सपोनेंशियल होता है job 1 क्लाउड्स में क्या है? क्लाउड्स में क्या ये सिंपल वो जो पॉइजन डिस्ट्रीब्यूशन यूज नहीं किया डायरेक्ट रैंडम
आउट फंक्शन के अंदर ही काम होगा
schedule we will feed all this information to the schedule until the response job notice that any set of stages that are included which is always given उसमें क्या पहले
ई कॉमर्स और पावर ई की
ई की वैल्यू 2.7 होता है multiplying doesn't share
माइनस लैम्डा की वैल्यू कौन सा है टी नॉट से मल्टीप्लाई टू 2.7 minus lambda into 0.5 per kilo lambda
before taking this decision.
ये टीम लेकिन ये वैल्यू तो चेंज होती रहेगी ना इस पे वेरिएबल के अंदर नेक्स्ट टाइम
in which way the allocation is where we are different how are we going to get so schedule determines so all this is our schedule calculates when it is which कुछ
नेहरू प्लेस जाएगा क्योंकि जब तक वो सही होगा उसमें मज़ा नहीं आएगा ऐसा तो बहुत टाइम
सर ये बोला जो एक ही
जैसे टू आ रहा है ये सारी डिपेंडेंट टास्क हो गई हैं जैसे डायग्राम बनाते हैं ना बहुत सारी डिपेंडेंट टास्क होती हैं बहुत सी इंडिपेंडेंट होती हैं जो डिपेंडेंट टास्क है वो ये सारी जिनका टाइम सेम और जो 3 जैसे 2 और 3 अलग हो गई तो ये सारी इंडिपेंडेंट टास्क
यानी नंबर ऑफ जॉब एक जॉब ये हो गया
नंबर ये चीज़ लिख लें अभी वैसे हम लोग रैंडमली कुछ लेते थे अभी अक्सर कह रहे कि पेपर रिजेक्ट किसी वजह से कर देते हैं कि इसमें ऐसे मौजूद नहीं है
जो नंबर ऑफ टास्क 10 फिट किया
These are the standard for queries.